Alright, today we're going to introduce the polar coordinate system. In the polar coordinate system, instead of just defining a point by x and y, we define it by r and theta, where r is just some distance from the origin, and theta is just the angle swept around, and this is the sweeping motion, from the positive x-axis. And even though these are written as r then theta, your hint here is to always sweep to the angle first. Always take care of theta and then worry about r, the distance from the origin. Alright, let's practice plotting some points. Alright, so we're going to plot these points A, B, and C, and D, remembering that each of the points is written as r and theta. And we're always going to sweep to the angle first. Here we have a positive 7, positive pi over 6. So I'm going to start by going to the angle of pi over 6. That's along this line. And then from the origin, I'm going to count out 7 in the positive direction. And that just means count the number of rings. So we're going to count out 7 rings to this point right here. For B, we're first going to go to the angle negative pi over 2. So whereas pi over 2 is right here at 90 degrees, we're going to go negative 90 degrees to this angle right here. Then we're going to count out from the origin positive 5. So from the origin on this angle, we're going to count out 5 rings to get our dot right here for B. C is at negative 6 pi over 3. So this time we have a negative r. So I'm going to go to this angle pi over 3, which is right here. But instead of counting out positive 6 in this direction, I'm actually going to go in the opposite direction and count negative 6. So I count out negative 6 rings, and so point C is actually right here. Notice that points B and C we could have written differently. Whereas this was 5 negative pi over 2, we could have written that as 5 3 pi over 2. Right? I mean, that's the angle 3 pi over 2, and we counted out positive 5. Or here, this is a positive 6 direction if we were on the angle 4 pi over 3. So the polar coordinate system is special in that there's not just one way to write each point. Unlike the rectangular coordinate system that you're used to, where every xy is very unique. Alright. This last one, D, you try to plot this point, and then we'll compare our answers. Alright, hopefully you're right here on pi over 2, because from this positive x-axis, we swung around negative 3 pi over 2, and then counted out positive 3 in that direction. Let's think about this. What would the graph of r equals 2 look like? Notice that this doesn't have anything to do with any thetas. So r equals 2 would actually just be a circle with a radius of 2. Just right around that second ring. Alright, what would the graph of theta equals 2 look like? It may actually be easier for us to first think, what would the graph of theta equals pi over 4 look like? Notice that this doesn't have anything to do with any radius, just theta is always pi over 4, either in a positive direction or a negative direction. So theta equals 2, well, 2 pi over 3 is about 2.09. So 2 would just be just under that. So theta equals 2 would look something like that. Now here's something interesting. The polar coordinate system, this system that we've just been looking at, sits right on top of the rectangular coordinate system that we're used to. This means that we can convert points between the two systems. Alright, so for any point xy, in math we have other ways that we can define where this point is in space. One way that we can do it is say, how far away is this from the origin? We'll call that r. We'll say it's a radius. But a radius can spin around a circle. So the other way that we define it's exactly right here is we say, and it's at this angle from the positive x-axis. So we're going to define it by r and theta. Now we could actually build a right triangle off of this, and we could say that this is the distance x, this distance y. And from this we can build a few important and helpful equations. So from this we can see that the cosine of theta would just be the adjacent over the hypotenuse. So r cosine theta would equal x. And by the same token with sine theta, we could say that r sine theta is equal to y. Now hopefully this is starting to look a little bit familiar. We could also find r if we knew x and y by saying x squared plus y squared is equal to r squared by the Pythagorean theorem. And to define this theta, we could say that the tangent of theta was equal to y over x. So theta is just the inverse tan of y over x. This look familiar at all? Hopefully so, because this is exactly what we use for vectors. Alright, so let's practice converting some points. Alright, this time we're given r and theta and we're told to find x and y. So we're given r is 5 and theta is negative pi over 3. So to find x and y, x is just r cosine theta. And y is r sine theta. Now at this point I'm going to use this unit circle to find what the cosine and sine of negative pi over 3 is. So at negative pi over 3, it'll be right here. The cosine is a half and the sine is negative 3 square root of 3 over 2. I'm going to put that away for a second. So we have 5 times 1/2 and 5 times the negative root 3 over 2, giving me 5 over 2 and negative 5 root 3 over 2. So the point 5 negative pi over 3 in terms of r and theta is the same point as 5 over 2 negative 5 root 3 over 2. On these two examples, I'm given x and y, and I need to find r and theta. For any point that's just on one of the axes, like here, negative 3, 0 is right here. Hopefully here you can see that this is 3 out from the origin, so r is just going to be 3. And that angle is at pi. So we don't really have to do any use any of these formulas for this, although we could. Now 4, 3 we know is in the first quadrant. Let's actually figure out r and theta. So to figure out r is the square root of x squared plus y squared. So r is going to be the square root of 16 plus 9, which is the square root of 25. So r in this case is equal to 5. To find theta, theta is equal to the inverse tan of y over x. So we're going to do the inverse tan of 3 over 4. And because we've been dealing this whole time in radians, I'm going to leave this in radians. So this is going to equal 0.644 radians. So the point 43 is at the point 5.644 in polar. Alright, that's the polar coordinate system. Goodbye.